Welcome, folks. We are now on to chapter 21, Polymers and Plastics. If you're following along in the book, the demo they have in the book is you get to see me separate some polymers based on their density. That's not really fun. How about we actually make some polymers? Well, I'm going to take some liquid latex, show how to polymerize this rapidly into rubber. That's what I'm going to do right now. Okay, so what I have in this little crucible is liquid latex. It may not look like much, but this green gelatinous goo is just unpolymerized rubber. Essentially, what we'll talk about in class, it's isoprene. It's actually a 2-methyl 1,4,1,3-butadiene, and that it has some ammonia in there to help keep it stabilized so it doesn't polymerize on its own. What's going to happen is that when I add some acid, it will become a polymer. Right now it's just a bunch of monomer that's all mixed up and it's all liquidy because it's all just individual chemical molecules. Add some dye to help with the visualization. Liquid, wipe it off, leave some green dye behind. But start by adding just a little bit of acid, because as we acidify this, well, first I'm going to add what has happened to the liquid. It becomes hard or a sleeve. Peels right off, as opposed to as long as there's acid on it, allows it to polymerize. So I'm going to add just a little bit of acid, see what we got, see how it goes. Just a pinch. So this is very organic, and the acid is very aqueous, so it's not quite mixing. So I have to physically stir it, trying to mix this up. I could mix it violently, but I'm trying to create a long polymer thread. I mix this up, coming into a gelatinous ball. Now, as what's actually happening here, as you can see, it's kind of encapsulating the vinegar. So there's vinegar pockets stuck in here that are not fully being mixing. So it's kind of forming into a ball, but not quite. Let's add a little bit more vinegar. Keep playing with it. Pull it around. And we have the liquid coming into a sticky polymer. So the polymer is known by the fact that it has large amount of monomers stuck together. So what we have now is a very bouncy latex ball. I'm trying to squeeze out the vinegar, and I'm going to eventually wash it to get it clean. We have essentially a vinegar ball. I could add maybe a little bit more latex to the surface, try to even it out, but right now, actually just latex. Before a nice ooze, we have a pencil ball made out of a natural rubber. One more time. last thing to show you. This is what happens to normal latex. It was originally white, but over time it starts to oxidize and corrode. What happens is the oxygen can do several different things depending on what type of polymer it is. That it can either cleave some of the polymer bonds together, causing them to soften, or cross-link some of the polymers together, and thus harden the bond. So if it starts to crack, it could be as it's hardening, but if it, the way this is what results in the discoloration of our bond. So that is forming a little polymer right before your eyes. I'll see you back in the lecture. Humanity has undergone a variety of ages of man. We've undergone Stone Age, Bronze Age, Iron Age. Well, what current age is often referred to as the plastic age. That plastic is all around us. It's used in packaging, bottles, containers, textiles, plumbing, building materials, furniture, flooring, paints, glues, electrical insulation, auto parts and bodies, all sorts of technology such as TVs, computers, cell phones, medical equipment, and a whole slew of personal items. All these contain plastics. It makes up so much of our life that even though this is a lightweight material most of the time, it still makes up 12% of all landfill waste. Globally, about 367 million metric tons produced in 2020 alone. About half of this goes into packaging and building material. Another 10% of this goes into personal care, and the rest goes into just about everything else. And so all these have a wide variety of properties depending on how you build them. They can be durable or fragile, rigid or flexible, sturdy or flimsy, dense or light, strong or weak. Plastics are very, very cheap and very easily modifiable to get the optimum properties. At the root is the whole idea of a polymeric molecule that make this up. But first we have to define and explain the differences between the idea of a polymer and a plastic. So we're going to go about polyethylene, especially low density polyethylene versus high density. Low density is low melting, very flexible, very soft, very low density, like trash bags and squeeze bottles and food wrappers and electrical cable wiring insulation. High density is rigid, higher melting, stronger, less flexible. Sturdy bottles and jugs like milk and water, and you drop your milk, you don't want it to explode. Engine oil, antifreeze bottles, gasoline tanks, polyvinyl chloride, which is tough and very resistant to oils. We use that in things like garden hoses and wallets and purses and key holders and shampoo bottles, and there's blister packs and run of plumbing and pipes known as PVC. Polypropylene can retain its shape at temperatures well above room temperature. It doesn't melt easily. So automobile trim, battery cases, food bottles, caps, carpet filaments. Polystyrene, lightweight and can be converted into a foam. It's insulation, packing materials, or plastic peanuts and what have you. Polyethylene terephthalate, known as PET. We can draw that into strong, thin filaments. Those are going to be food packages and backing for magnetic tapes and soft drink bottles. Gases can't get out. Phenol formaldehyde resins like Bakelite, strong adhesive, plywood, fiberboard, insulating materials, and nylon, easily drawn into strong, thin filaments. We use synthetic fabrics and fishing lines. These are just typical applications of a lot of different plastics. The first thing we need to do is to define a plastic. Plastic is a material capable of being shaped into virtually any form. It comes from the Greek plastikos, substance suitable for molding or shaping. So plastic can be shaped into balls, into thin fibers, intricate parts, or thin films. It all depends on what it's going to be used for. Now, this This is where a polymer can shift from the field of engineering to the field of chemistry, because proteins, starches, and celluloses are polymers as well as plastics. Cotton and silk and wool are all examples of polymers. DNA is a polymer. Well, polymer is Greek for polymeros, many parts. A polymer is simply a molecule of very high molecular weight formed by the repeated chemical linking of a great many simpler, smaller molecules. So polymers are an example of what we call a macromolecule, but are usually formed by the combination of anywhere between thousands and millions of what we call monomers. A monomer is an individual structure that are linked together to form a polymer. So like a protein is made up of thousands of amino acid monomers. Sugars, complex sugars like cellulose, are made up of many different simple sugars. A polysaccharide is made out of many monosaccharides like glucose. I think on the DNA is deoxyribonucleic acid. When that it has a simple sugar backbone with the nucleic base and a phosphate group. That all that goes in into a repeating pattern with slight variations. Now, these polymers could be in many different forms. It could be a linear chain like the one on the bottom left, or they could be a very branched and interconnected like we see in the bottom right. They can form a web or rigid 3D lattice depending on how they're connected. But these polymers are usually formed as long chains or sheets. The plastics can then be readily molded into any shape. With polymers, polymers don't have to be plastics, and polymers, as we'll see later, don't even have to be organic, but many of these are organic. So how does one go about polymerizing in the first place? So polymerization is the process whereby individual monomers will link together to form a polymer. Now, there's two main types of polymerization reactions we'll talk about. One is addition, the other is condensation. Like polyethylene is a type of addition reaction. We see this in the two left-hand sides. There's two ways to think of it. Ethylene is a CH2 double bond CH2. What could happen is the double bond can split in half into two electron pairs, which can then one goes to one ethylene and the other goes to another ethylene, and two electrons meet, they form a new bond, and so they form a linking chain. Or you could think of it as the two electrons from one double bond donate directly into the next atom and move on like a chain. So whether it's a split in half or chain your way through, that is a simple addition polymer. On the other hand, a condensation polymer is a losing of a simple small molecule such as water when two molecules combine. That when, like, say, an OH and an H meet, you can lose water. But it doesn't have to be water. It could be ethanol, it could be something else. But the idea is we form a polymeric linkage. Glucose in the upper right, I think it's the 1 carbon hydroxy group and the 4 carbon hydroxy group combined together to form the glycosidic linkage. So for those people who will see any biology in the future, that may come up from a glycosidic ether linkage that combines our sugars together. Amino acids do the same thing. Amino acids have an amine group, which is an NH2, remember, and an acid, which is a C double bond O, OH. When they combine together, you lose the OH from the acid and the H from the amine to form an amide linkage in a protein. Nylon, which we'll talk about later, is another such example of a condensation polymer, as is PET, which I've shown down there, that we have acid, a diacid, and a dialcohol that condense to form that ester linkage. But we can think of polymers as two basic types, one of which is a homopolymer, as we see here, where we have one chain linkage that just repeats over and over and over, that there's no differentiation. It's just this link connected, this link. And we can simplify it down to simply that link with N being the number of repetitions. So polyethylene with that CH2 you see right there is an example of a homopolymer. It's made of repeating CH2 groups. A copolymer, well, homo comes from the Greek homos, which means the same. So the copolymer is when it varies. We combine two different groups over and over and over again. So XY, XY, XY. Many condensation polymers do this. PET is an example. That molecule right there with the six-membered ring and the C double bond O on both sides is one linkage, and the O CH2O makes up the other linkage. That this repeating group is going to repeat over and over and over again. And so XY, just like you'll see in nylon, it's two groups combined together to form one repeating unit. But now the repeating unit can be simple or it can be complex. That whole six-membered ring for sugar is the repeating unit, with that O being part of that O coming out being part of that repeating unit. It's going to repeat the same over and over again. And we can simplify that down rather than drawing a whole mess of the products. Now, the properties of a polymer can be varied based on how it is made and the monomers used. But we can also separate it into how it reacts when heated. A thermoplastic, which is the large variety of plastics, will soften when they're heated, but then harden again when they cool. So if you took a water bottle and heated it up, you could melt it in half. It would soften up and you could just bend it right over and then cool it down. And it can harden into whatever shape you set it up. But a thermoset kind of works the other way, that they will hold their shape even when they're heated. You heat them up at the very beginning, you form it into whatever place, and then you heat it up and it sets into that shape. So it's soft, you heat it and it hardens and it doesn't leave it. Bakelite, which we'll talk about in a bit, is an example of a thermoset polymer. Bakelite is an example of a strong polymer that is a poor conductor of heat and electricity. It's used in many handles and toasters, pots and pans, wall outlets and adapters, even billiard balls. But most common plastics are thermoplastics. Another type of plastic we could look at is elastomer. Polymer is elastomer. Elastomer was brought back to Europe by Christopher Columbus, where he found the natives, South America, playing with rubber balls, a natural type of platinum polymer. They could form that into the heavy bouncing balls that could ricochet all over the place. But it's a simple polymer that is made, addition polymer made of isoprene. So you have a 1,3-butadiene that's substituted at the 2 position with a methyl group. This polymer, when it does an addition, the double bond from the 1 position jumps to the 2 position, and the 3 position double bond goes into making the next bond. So we can be a chain that has a series of double bonds intermixed into it. And because of the double bond that forms in the center, we can actually create what's called an isomer. These isomeric linkages, where depending on where the double bond is, you could either have that methyl group being on the opposite side of the chain or on the same side of the chain. So we could have all the methyl groups pointed up, or every other methyl group facing the other direction. So we can look at what's called the cis isomer, which means the same side, or the trans isomer, which is the opposite side. The cis isomer is just normal rubber that it's very, very bouncy because of all how it's put together. The other one, the trans isomer, forms a slightly different version called gutta percha, which I'd never really heard of until really reading through this, but it can be formed naturally through, there's a gutta percha tree, but you can also form it normally through this method, and it's a far less bouncy, and it's biologically inert, and it's often used because it's a good insulator. But it's found its uses in some things like pistol grips, which we no longer use that. We use other types of plastics. Golf balls is a good example of where we use gutta percha because we don't want it too bouncy. We don't want to go flying all over the place, but we do want some amount of bounce. And certain types of surgical equipment and underwater cables they're biologically inert. So we don't have to worry about bacteria getting at it. The difference in elasticity depends on the physical structure as much as it does the physical properties. The ability of a molecule to coil up between the various chains is what contributes to the springiness. When rubber is heated up, the strands can actually slip past each other and it becomes more sticky and less bouncy. So if you look at the top picture over there, over here, this is all the rubber strands. They're all tied together and they have some bounce, and then they kind of like bounce off each other and kind of spring back. But when it's heated up, they can slip past each other, and so they're no longer attached and they're no longer bound together, and so it's no longer bouncing off each other and becoming springy. So rubber tires that haven't been vulcanized become sticky as they get hot rather than bouncy. Well, people wanted to try to solve that. They wanted to try to make sure the tires didn't go bad with large amount of heat. So that introduced Charles Goodyear on the picture up top, born in 1800 in New Haven, Connecticut. He solved this problem partly by accident. He was trying to solve it, but it's just one of those types of serendipity again. Unfortunately, he's never going to be able to capitalize on his invention. So he was obsessed of the idea of creating rubber that retained its elasticity when hot. He even spent time in jail for debts accrued during his search for this, back when debtor's prison was a thing, and then you could go to jail just for owing money to someone. After 10 years, he got lucky when he accidentally dropped a mixture of rubber and sulfur onto a hot stove. The charred mixture stayed bouncy even while it's warm, so no longer sticky. He didn't understand why. This is he only understood that it worked. This is a perfect example where technology has surpassed the science. We didn't know why. A lot of this early polymer work, we don't know why it works. We didn't know why it works because we didn't fully understand polymers. We just know, I made this cool thing. Hey, let's deal with it. He dropped it on. I don't know why it works. I just know that it's still springy. I know it only works when I mix sulfur and heat it up. So this process, we actually know now that this process causes a cross-link between the molecules. The sulfur binds the strands together, meaning that when it heats up, they can't slip past each other. They stay entangled, and so it retains its bounciness, creating a nice 3D lattice. While Goodyear did obtain a patent, he failed to make his fortune in America, failed to make it in England or France. He was in and out of debtor prison, eventually died in poverty in 1860. That's kind of sad. Well, so it goes in the process of invention. This process, though, was called vulcanization, after Roman god of fire and crafting, Vulcan, also known as Hephaestus in the Greek mythology. We still know about Goodyear's name because of such people like Frank Sieberling, who founded the Goodyear Tire Company and honored him in 1898. So founding the Goodyear Tire Company, and we know about the Goodyear blimp because of that process. He actually made money off of it. But nowadays, we supplement the natural rubber with, or replace it all together with mixtures of things like butadiene and styrene. We'll see styrene a little bit more later to make a synthetic rubber. Another such one is neoprene, a polymer of chloroprene, which is 2-chloro-1,3-butadiene instead of the methyl group, which has a far higher heat tolerance and a far resistance to gasoline and lubricants. So this was developed by Wallace Carruthers, which we'll see more on him later. He's the guy who will invent nylon. But so that's an alternative that doesn't dissolve with gasoline. But down there, the bottom picture is Frank Sieberling, the co-founder of Goodyear Tire. Now, another polymer was invented as a means to replace a rare and quickly disappearing substance, ivory. By 1863, ivory was becoming a very valuable and expensive commodity, as elephants don't exactly reproduce very quickly. The firm Phelan and Collender, which was a manufacturer of ivory billiard balls, offered a $10,000 prize to anyone who could develop a substitute for ivory. Now, John Hyatt and his brother, we see John below, took up that challenge with a little help from an earlier discovery from 1846. In Switzerland, the chemist by the name of Christian Schobein, who's featured above, accidentally invented gun cotton when he spilled a mixture of nitric and sulfuric acid in the kitchen and proceeded to wipe it up with his wife's cotton apron, which, yeah, I don't want to have her come home to that. He rinsed the apron thoroughly and hung it to dry over the hot stove. So, like, oh, maybe she won't notice. But over the hot stove, the apron went up in an instant, disappeared in a sheet of flames. I'm sure his wife was super PO'd until she saw like how much money could eventually be made from this. He had accidentally invented smokeless gun cotton, which would replace the smoky gunpowder that we have known through the American Revolution and Civil War. It has several major advantages over gunpowder in that it burned cold, so that when you fired it in the barrel wouldn't heat up as rapidly. So you wouldn't like burn yourself on the barrel as easily. It burned clean, so not smoky. A lot of the saying fog of war was created by you get these people firing guns for any period of time. You're creating these smoke clouds that make it really hard to tell what's going on. And it burned after being moist. So you didn't have like, oh, it's a foggy, dewy morning, I can't shoot, I guess we'll have to do a bayonet charge. Now, unfortunately, it wasn't used in the Civil War despite having been invented, despite being invented before the Civil War, just due to its novelty and some of the dangers due to it burning too fast and too explosively. But what he did, he turned Schobein turned cellulose into nitrocellulose, pictured above, by turning the OH groups on cellulose into NO3 groups with the sulfuric acid as a catalyst. Well, John Hyatt would then combine this nitrocellulose with camphor oil. Camphor is this weird bicyclic molecule that you see below. It's used come from the camphor tree, and it's often used in oils and creams, sometimes used as like a decongestant, your chest rub, and other things. But when he mixes those two things together, he creates a thermoplastic very similar to ivory. We call this now celluloid. Hyatt managed to become financially successful with his product. And while it was too brittle to actually be used for billiard balls, which is what it was supposed to be invented for, it's used in dental plates, photographic film, ping pong balls, and more. Unfortunately, there is one problem, that it's very highly flammable, and that, like, especially when when it was used in the old movie projector reels, that if the projector got too hot, they could burst into flames and burn down the whole building. Now, while this was the first successful commercial plastic invented, it is not a true polymer. That we can't show you, I can't show you the structure of what that forms, because it's not a true polymer. But our next polymer is a true polymer, created by Leo H. Bakelite, who was born in 1863 in Belgium. He was an industrial chemist, teacher, and eventually would emigrate to the US and become a naturalized citizen. He even became the president of the American Chemical Society. Well, in 1909, he announced his new resin, Bakelite, to the world. Of course, he was very smart. He made sure he got his patent and made sure he founded his corporation to produce it first. So he's not going to tell everyone about it until he's ready to run with it. So he invents Bakelite, which is a thermosetting plastic, our first real thermoset, made up of phenol. You can see that up there, which is a 6-membered ring with the alcohol group, and formaldehyde, which is a C double bond O. This is an example of a condensation polymer, that we lose the oxygen of formaldehyde and the 2 hydrogens from phenol to form this weird 6-membered ring, where that we have a ring made up of rings. We have 3 formaldehydes are bound to each phenol, and this keeps going on and on and on. I'm only showing a small portion of this. Bakelite is a hard, sturdy material. It's resistant to heat and electricity, and it isn't easily burned or scorched. We can change the aldehyde to further modify the properties. It doesn't have to be CH2O. It could be something else. But its primarily use of this is a type of what we call phenolic resins. But the primary use of these are adhesives and fillers, especially in the manufacture of plywood and fiberboard. So we're using that to help stick the fiberboard together, and use of various insulating materials. Now, many of the polymers we see we've seen so far were part effort and part accident. We didn't quite understand the science. This could be done in a home lab. However, these type of discoveries are becoming less and less common in the 20th century due to the growing sophistication of science equipment and technique, the increasing rigor of the research within the academic, industrial, and governmental fields and labs, then the development of a comprehensive understanding of polymers and the structures in the 1920s. So basically, the science has caught back up to the technology. We just playing around. When we find something, we mix this together and it works. We don't know why. Well, now the science understands it, and so we can start, and we've already even surpassed it, and we can start designing our own molecules before we build it, knowing what should happen before we run the experiment. So one such person is William Carruthers on the left. He left his teaching post at Harvard University, so already prestigious, to lead a research group for DuPont Corporation in 1928. With a systematic study of how polymers form, he was quickly, a few years, able to invent nylon, which we see in the bottom left, by mixing what's called adipic acid and 1,6-diaminohexane. Adipic acid is the 6-membered diacid you see on the right, and the diaminohexane is the 6-membered carbon with 2 NH2 groups on the other side, each side. And once again, the OH of adipic acid and the H of the amine group form that amide linkage, much like in amino acids. Adipic comes from the Latin adipem, which is fat. Adipem, or the adipic acid, is formed through the oxidation of fat from nitric acid. That's just neither here nor there. So there's a condensation to form an amide. By alternating groups, they can form the polyamide, which is a copolymer. They managed to make several different types of nylon by using various different acids and amines. I'm just showing you one. But this was first used in 1938 as a toothbrush bristles. So they didn't really realize its true capabilities at first. But in 1939, it became a commercial success as it replaced the more expensive silk stockings. So the name nylon is actually a modification of no run, which was its one of its key advertising features. It was no run stockings. You're not going to develop runs in them. But that was deemed an unacceptable name, so they reversed it and so new ron, and then changed it to nylon from there. But in World War II, the military used nylon in just about everything. They had nylon ropes, various other supplies, so much that the civilian quantities were rationed. And the stockings were in such high demand and so rare that they became a informal currency in Europe till the early 1950s, when we could finally catch back up with production. Another such designed polymer is the industry invented condensation compound PET, which is polyethylene terephthalate. So they use the ethylene glycol, which is a dialcohol, and terephthalic acid, which is a diacid, the phenyl diacid. In 1941, John Rex Winfield would invent this, calling it Dacron, which in the US, and it's some other names in different places, but essentially it's almost in all our soft drink and food containers. That's one of its key uses. So that's the last of the copolymers we're going to talk about right now. The next few polymers are all polyolefins. Well, polyolefin being a polymer produced by the polymerization of alkenes and compounds closely related to them. Polyolefin is actually a corruption of the word ethylene by several Dutch chemists in 1795, referring to an oil-forming gas, or ethylene. But as an alkene, olefins will form via addition reactions. So we're going to move those double bonds from one atom to the other to make new bonds. However, many of these will have substitutions at one or more of the carbon compounds, creating a large variety of properties. So by replacing an H with a phenyl group, for example, we form styrene. And from styrene, we get polystyrene. So that at the bottom left. Polystyrene first discovered in 1839. It wasn't really produced industrially to the 1930s and 40s when styrofoam was then patented. So like anything styrofoam container, styrofoam coolers, all that didn't really come to the 1930s and 40s. Styrofoam was patented in 1944. A lot of these things, people screwing around in the lab, find it in the early 1900s, and then it gets used in the 20th century when we finally understand more about it. There's a bunch of different ones here. Vinyl chloride is another name for ethylene chloride. Will become polyvinyl chloride, PVC. As I said, a tough plastic suited for pipes and plumbing, flooring, and all sorts of commercial uses. However, PVC is a very hard substance, and so we actually have to use a plasticizer in there. A plasticizer is a liquid that is added to soften it up to prevent it from cracking. But eventually that plasticizer does migrate and get lost from the PVC. So over time, it will become brittle and start to crack again as the plasticizer runs out. You have things like here in polyvinyl acetate, coming from vinyl acetate, which is used in Elmer's glue and safety glass. And that you stick a layer of polyvinyl acetate between two sheets of glass, and when the glass shatters and when cracks and fragments, you don't have glass shards embedded in your chest. So when you get in a car accident, it doesn't just immediately cut you to shreds and kill you. It also can be added to gum. You add sugar and the PVA, and you're chewing that, and essentially chewing a polymer that keeps the gum chewiness and doesn't degrade. Polyacrylonitriles is used in many synthetic fabrics. Vinylidene chloride It's used to make saran wrap. That is essentially, it's very good at blocking out odors. Where it has 2 chlorides instead of 1. Tetrafluoroethylene. So we have 4 fluorine groups on it. Forms the nonstick product Teflon. Methacrylate is used in lucite and plexiglass. So all of these guys are just an example of addition polymers where we just substituted one or more of the carbon groups and we allowed this to combine together. Now, one of the ones we have kind of saved for last is actually one of the simplest ones, polyethylene. Now, polyethylene is the simplest to make and the largest percentage produced. I think I got a number, 22.67 million tons made by the US in 2019 alone. So it's very simple. The properties can be established by controlling how the strands actually assemble and the length of the polymer strands in itself. It was first produced industrially in 1934 in the UK as electrical insulation in military radar installations. So they used and coated the wires so you didn't have shorts and you didn't have, and kept the radar running. And the book goes on to say, oh yeah, because of that, because we needed the radar so early to help prevent the warn people the bombings in England, it saved the war. But man, I'm not going to make such assumptions, but probably true. Now, it's later found out that this is actually, we now call that early polyethylene as LDPE, or low density polyethylene. It's named that because it develops branching errors, that you have a misaddition, that we allow it to grow naturally. Sometimes errors will build into the radical mechanism and will build these branching regions on there. And these branching regions will keep the strands from getting too close together. So we won't get a good surface contact. And so it'll be more random. So it'll be like a ball of fuzz rather than some coherent crystal. This will make it low density because it can't pack as tightly. It will make it softer because you have more wiggle room, and it'll make it lower melting point and more flexible. Because the harder it is to get interactions together, the easier it is to separate into liquids. This is the type that's used in our various bags, wrappers, packaging, and electrical insulation. But in the early 1950s, a chemist by the name of Carl Ziegler up top, who looks like Walter White, German Walter White, found a way to polymerize the polyethylene using an organometallic catalyst. So breaking that down, a metal catalyst with organic backing will help control the growth in a very systematic fashion. It controls how it adds, so it prevents any branching from occurring. And because of that, you get regions of crystallinity within the structure, and so it can pack more tightly. So it gets a harder, more dense, more rigid, higher melting point polymer called HDPE, or high density polyethylene. These are used in various bottles that we need to be more sturdy, like bleach, antifreeze, oil jugs, milk. It's used in fuel tanks and folding chairs. You don't want to drop a folding chair on the floor and watch it just snap in half. You don't want to drop your bleach and suddenly the bleach bottle explodes and spills everywhere. So we want high density, the harder, more rigid structure. And we've already seen in this chapter how molecular geometry controls the structural properties. We've seen how butadiene can polymerize from the cis isomer to make rubber, or the trans isomer to make gutta percha. We've just seen that in polyethylene, the high density has no branching, and the low density has branching, and you have different properties there. Well, in chiral molecules, which are molecules that will polarize light due to their handedness. So basically, a chiral molecule has a has a different orientation that can make it a mirror image of a different molecule, but they won't fit. It's like having a left-hand molecule and a right-hand molecule. They look the same, especially in a mirror, but they are not the same. If I put them together, I can't replace my left and my right without knowing that they're in the wrong places. So we have certain chiral molecules. They can bond together when they polymerize in 3 different ways. Each atom can bond identically with a substituent coming out the same side, and that's called isotactic. They can bond in alternating sides, which is called syndiotactic, or they can bond at random, which is called atactic. These names come from the Greek taktos, which means ordered, and iso, meaning same ordered, syndio, 2 together ordered, and atactic, not ordered. Generally speaking, not ordered would be like our low density polyethylene when we don't exhibit extensive control over the crystallization. This is what you get, a not ordered situation. It's very random. It's every now and then it's one way and then it goes the other way. But the very ordered structures have much better properties. So in 1953, Carl Ziegler again and another Italian chemist by Giulio Natta developed independently a class of organometallic catalysts that can form highly ordered isotactic and syndiotactic polymers rather than the atactic that we're maybe more used to. They would end up sharing the Nobel Prize in 1963 for this work, and we now know about the Ziegler-Natta catalysts. But these highly ordered polymers are far more crystalline. They are typically harder, and they have higher melting points that they're not going to decompose as quickly. Now, the last type of polymer we'll talk about aren't plastics at all, but they're actually a class of inorganic silicates. Silicon is a tetravalent molecule like carbon. Tetravalent means it forms bonds with 4 other atoms. But while oxygen is divalent, hydrogen is typically monovalent. So CH4, each hydrogen wants to bond with 1 carbon, and carbon wants to bond with 4 hydrogens. But with silicon oxide, these silicates, each oxygen wants to bond with 2 atoms, and each silicon can bond with 4. And so because of that, we can form a variety of double-stranded tetrahedrons bound together so that each oxygen is shared between 2 different silicons. And like, depending on how these tetrahedrons arrange themselves, we can have various different properties. We form like a double-stranded tetrahedron like the one on the left, which is asbestos, which is a flame-resistant insulation that's now shown to form mesothelioma, which is a cancer of the lungs. Basically, they used to coat this in buildings, so when a fire happened, it wouldn't burn. It doesn't burn. Only problem is that when it's a paste, it's perfectly safe, but when it dries, it becomes like a fiber insulation that if you breathe it in, it attacks the lungs and weakens them and make you develop cancer. So it's no longer in use, but it used to be everywhere. If it forms various 2D sheets, you could be responsible for micas, talcs, and clays. But if it forms a full 3D lattice like you see on the upper right, it's responsible for quartz and other various gemstones. Like amethyst is quartz mixed with some various impurities to give it the color. So silicates are responsible for a lot of different types of crystals. Now, one of the major issues with plastics that we haven't really discussed is their biodegradability. A biodegradable substance is a substance that can be easily converted into simpler substance that can reform our natural environment, whether that's by microorganisms or something else. But so when we eat meat, we have bacteria in our stomach and our acid that help break the proteins down into simple amino acids that can be utilized by our body. It breaks down our complex sugars, which are polymers, into simple sugars that can be utilized by our body. Well, for substance to be biodegradable, we need to break down these large polymers or plastics into simpler monomer chains that can be utilized by whatever is using them. So many of these are too complicated to degrade easily. And burning, some of them can be burned as fuel, but besides producing lots of carbon dioxide gas, some of them like Teflon and PVC will produce toxic gases like fluorine gas and chlorine gas, which are not really good. So recycling is only so effective. We only recycle a small fraction of these. And even then, it's not like glass, which we can just put right back into production. Some of these, you can't really just recycle them. Like this was a milk jug before, we turn into a milk jug again. So we're kind of stuck. But work has been done into finding more biodegradable plastics, ones that are maybe naturally produced and easier to break down. But there's also been a lot of work into the avenue of finding or developing a bacteria that digests plastics. And it seems like there is a lot of them that have been found. They're finding some more that have been either evolving due to all the plastic we're putting in our environment, or they were always there along, but they have certain enzymes that are capable of at least breaking down certain linkages. Like there's one that can break down the polyester bonds, thus separating the PET down into simple molecules that could be digestible by the bacteria. So being able to use those might be able to help solve some of our problems, but that's still a little bit into the future. It's one of those things we're always catching back up to the mistakes we have made. That is our chapter. Our discussion prompt for today is another one, the short one. In 150 words, I want you to try to consider our plastics again. I want you to consider comparing the benefits of these various plastics versus the difficulty of their disposal. Do the benefits outweigh the problems they generate? Obviously, we didn't really spend too much time just talking about plastics. So you're going to, the disposal of plastics. So you're going to have to take what knowledge you already know. Think about the plastics in our environment. Plastics, well, I mean, you can look a little bit about how we're currently getting rid of them, but think about that. Think about all the good properties we've talked about this chapter. Do the fact that they're cheap and easy, and the replacements for a lot of the stuff we have that without plastics, probably wouldn't have a cell phone. Without plastics, your car would be 100% more unsafe. So think about that. So considering the benefits and the difficulty with the problems, considering the benefits and the problems, do the benefits outweigh the problems? So try to back this up with your evidence, your opinion. Don't just say yes. You obviously have to back this up to get full credit. Okay, that's what I have for you today. Have a good day.